So consider these 4 sets of quiz scores from 4 different sections of a class. A quick calculation will discover that the mean and the median of each of these data sets is 5. And yet, looking at them, you can tell that they're quite different. And so for this, we're going to need to talk about not measures of center. In this case, they all have the same measures of center. But instead, we're going to need to talk about how spread out or how varied the data is. And so we're going to talk about a range of measures, the first of which is called the range. And the range simply measures the difference between the biggest value and the smallest value. So it tells you how much the data ranges over the entire set of data. So here, my largest value is 5, my smallest value is 5, which means this data has a range of 0. And that's really important, because that tells me that the data is all the same. This data has a range of 10, right? It ranges from 0 to 10. And so that means it is quite spread out from its smallest value to its largest value. Let's see here, this data ranges from 4 to 6, and so the range here is 2. And this seems to be capturing pretty well how spread out the data is, until we look at this last set, where the range is also 10. But if we look at this data set and this data set, we can see that they're quite different. This set, half the class failed and half the class got perfect, whereas in this class, we had 1 failure, 1 perfect score, and a lot of people right in the middle. And so, while the range is a useful measure of center, we would eventually like to have a different measure, or a more specified measure that looks a little deeper than just the range of values. So next, we're going to look at a different measure of spread called the standard deviation. And so we're going to be measuring deviation or difference from the mean. And so the first thing we're going to need here is the mean of these scores. And the mean of these scores turns out to be 5. And so what we're going to do here is look at our data and then the deviation. In other words, the difference between the data and the mean. How far each of my data values is from the mean. So for this data set here, let's see, we got 0, 0, 0, 0, 0, 10, 10, 10, 10, 10. So the deviation here is data minus mean is -5. And I think you can trust me that all these other zeros are going to be the same. And then for the 10, 10 minus 5 is 10 minus 5 is also 5, positive 5, and so on down the line. Now, we want to find some measure similar to sort of the average of our deviations. The problem is that if we added these all up, they'd add up to 0. And so we need to do something else, and there's a couple approaches that we could use. It turns out the one that makes the most sense is to square the deviations. There's various reasons for this, but most simply, it will definitely make the values positive. So -5 squared is 25, 25, 25, 25, 25, 25, 25, 25, and in this particular case, it's very easy to calculate, too. And so we find all of our deviations there. So now we're going to find the sum of those squared deviations. So we're going to add all these up. Let's see here, I'm adding up 25 10 times, right? So that ends up being 250. So we're going to find the sum of the squared deviations. Actually, I'm going to write that down here, 250. And then I'm going to divide it by not how many, not by how many, okay. Well, what we divide by depends upon whether our data was coming from a sample, in other words, from a sampling of all of the data, or whether it was representing the whole population. So, if it's the population, then we divide by n, the number of data. If it's the sample, then we divide by n minus 1, 1 less than the total number of data. In this case, this is representing the entire section's scores, and so we're going to divide by n. We're going to divide by we're going to divide by n. We're going to divide by the 10 scores, and we're going to get 25. Now, at this point, we have something called variance, or more specifically, the population variance, since this was for the entire population. The standard deviation is the square root of the variance, so it's the square root of 25. Square root of 25 is 5, and so the standard deviation of this data set is 5 units. Now, for comparison, let's look at all of our other data scores. When all of our scores are the same, the deviation is going to be 0. The data set we just looked at had a deviation of 5. In this case, all the scores are much closer to the mean, and so the standard deviation is going to be smaller. In this case, even though we had the same mean and median and range as our data set B, the standard deviation here is much smaller because most of the data is very close to the mean, and we only have a few values that are further out. So if the data is very spread out, we have a big standard deviation. If the data is closer together, we have a small standard deviation. So we have 8 male students' weights in pounds recorded here, and we're going to find the standard deviations of these weights. And just to be clear, this data was a sampling, and so we're going to use the sample standard deviation here. So the first thing we need to do is find the mean of our data. And so to do that, we'll go ahead and just add up all of our data. So we add up all of our data here, which adds up to 1,400, and divide it by the number of data values. We got 8 data values, and we end up with a mean of 175. So now we can take each value and find our deviation from the mean. So for the weight of 165, the deviation would be, that's not the right number, it should be the mean. Minus 175 is negative 10 is our deviation there. For 145, we got 145 minus 175 is negative 30. For 160, we got negative 15, and so on for the rest of the values. So now that we have all the deviations calculated, now we can go and find our squared deviations. So we're going to do that by squaring each of these values. So negative 10 squared is 100. Negative 30 squared is 900. 15 squared is 225. 25 squared is 625. Sorry, negative 25 squared, but when we square it, it becomes negative. It becomes positive. 5 squared is 25. 45 squared is 2045. 25 squared is 625, and 5 squared is 25. And now we'll go ahead and add all those up, and the sum of all of our deviations is 4550. So remember that standard deviation is found by finding the sum of the squared deviations, and then dividing by either n or n minus 1. N if it's from the population, or n minus 1 if it's from the sample. So we're going to take our sum of squared deviations here, and because this is from a sample, we're going to divide by n minus 1. So we're going to take our 4550 and divide it by 7, which is 1 less than our number of data, which was 8 pieces of data. So we go ahead and divide that, and we end up with 650. Again, that's what we call variance. And then our standard deviation will be the square root of that variance. So the square root of 650 is about 25.5. It's actually like 25.4951, but again, typically we round to one more decimal place than our original data had. And so our standard deviation is 25.5 pounds. Standard deviation is measured in the same units as the original data. So there is the standard deviation. So we have a set of females' heights, and it's been sorted from smallest to largest, and we want to find the 5-number summary. Now, the 5-number summary is based on the median, kind of like the standard deviation was based on the mean. So this is a measure of spread based on the median, and the idea is that we're going to take all of our data. So suppose we have this big chunk of data, and we're going to divide it up into quarters. So we're going to divide our data into 4 chunks. And the median, remember, divides the data in half, right? And so the median will be in the middle. At the bottom, we'll have a minimum value, and at the top, we'll have a maximum value. Now, these two values are called the quartiles. This one is called quartile 1, or Q1, and this is called quartile 3, or Q3. You might be able to guess that Q2 is the median. So quartile 2 is the median. So we need to divide our data up into quarters. By the way, in some other situations, you'll hear quintiles, and quintiles divide the data up into chunks of 5 rather than quarters. So we're going to go ahead and see if we can find these. So minimum and maximum are pretty easy, right? Our minimum is here, our maximum is here, and our median, when we have 9 pieces of data, will be, let's see, it's odd, and so it's going to be the 5th piece of data, and so my median is here. So the main thing we need to find now is the quartiles. And so to do that, we're going to use something called the locator method. So we're going to calculate a locator. Now, remember that the quartiles are supposed to divide the data into quarters. And so we're going to figure out where is 1/4, or in other words, 25% of the data values. So in this particular case, 0.25 times 9, let's see here, 0.25 times 9 is 2.25. Now, if this comes out to be a decimal value like it does here, so if this is a decimal, then that means that the quartile value is going to be a single number. So then we go up to the next whole number, and we use that data value. So in this case, we're going to take this and we're going to go up to 3. Notice we're not rounding here. We're moving up to the nearest to the next whole value. And so the third data value is going to be our quartile 1. And so quartile 1 is going to be right here. It's our third data value. Now to find that's our first quartile. Our third quartile, we do almost the same thing, but we use 75% rather than 25%, because the third quartile is 75%, 75% of the data is lower than it. So in this case, that comes out to 6.75, and we follow the same rule. If it's decimal, we're going to go up to the next value, and so this would be the 7th data value. And so the 7th data value here is 5, 6, 7, this one, and that's our quartile 3. So to answer our original question here of find the 5-number summary, the 5-number summary here is those 5 numbers: the minimum, the quartile 1, the median, the quartile 3, and the maximum. That's our 5-number summary. So in the next video, we'll look at what to do if this locator does not come out to be a decimal. So in this example, we calculated a 5-number summary, and when we were using the locator method to find our quartiles, we looked at the case where the locator comes out to be a decimal value. In that case, we went up to the nearest whole value and used that data value. So now suppose that we had only 8 pieces of data. So the minimum and the maximum are still very easy to find. The median now, remember, if it comes out to be a whole number, then we're going to find the mean of the 4th and 5th data values, which is going to be 65, so that's our median. And now let's see if we can find our quartiles. So we're going to do the same thing. We're going to use the locator method, which means we're going to find where 25% of our data is, or for quartile 3, we'll do 75%. So here, if we do 25, that's not a 5. If we do 25% of our 8 pieces of data, we come up with 4, which is not a decimal value. So if this is not decimal, then we're going to basically run into the same thing we did with our median, where we're going to then find the mean of the Lth and L plus first data values, which is a fancy way of saying, like if we come up with 4 here, then we're going to use the 4th and 5th. So this value is going to give me the first one to use, and then we also use the next one in the list. And wow, I did not calculate that right. I'm sorry. 25% of 8 is 2, not 4. And so we're going to use the, let me correct that there. We're going to use the 2nd and 3rd data values. So if the 2nd and 3rd data values are here and here, so we're going to find the mean. Just to clarify, we're going to find the mean of the 2nd and 3rd data values. So the mean of 60 and 61, add them up, divide by 2, of 60 and 62 is 61. For quartile 3, we'll do the same thing. We'll use the locator method. So we'll use 75% of n, of our data value, and that comes out to be 6. Again, that is a whole number. It's not a decimal. And so we're going to need to use the mean of the 6th and next one, 7th data values. So let's see here, 1, 2, 3, 4, 5, 6, and 7. So 6th and 7th data values, we'll find the mean of those is 68. So our 5-number summary here would be 59, that's the minimum. 61 is quartile 1, 65 is the median, 68 is quartile 3, and 70 is the maximum. And that's the 5-number summary for that data. So let's go back to our quiz score data and see if we can find the 5-number summary for each of these. Now, each of these data sets has 10 pieces of data, and so using our locator method with 10 pieces of data, that's 2.5. That is a decimal, and so we're going to use the 3rd data value, for our quartile 1. Likewise, for quartile 3, let's see here, that's going to be the 8th data value is going to be our quartile 3. So let's see here, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 8, 3, 8, 3, 8. And so those are all of our quartile 1 and quartile 3 values. Now notice for our median, 10 over 2 is 5. That is a whole number, so between 5th and 6th. So we need to find the mean of the 5th and 6th values in order to find our median. So let's hear 1, 2, 3, 4, 5. Halfway between is 5. 1, 2, 3, 4, 5. Halfway between is 5. 1, 2, 3, 4, 5. Halfway between is 5. 1, 2, 3, 4, 5. Halfway between is 5. And actually, I think we already knew that, but oh well. And then, of course, we have our minimum and our maximums for each of these data sets. And now we can write our 5-number summaries. So for this data set, it is 5, 5, 5, 5, 5. They're all 5, right? Why? Because all the data is 5. Our next set is 0, 0, 5, 10, 10, which gives us a really good idea that 25% of the data is between 0 and 0. And 25% of the data is between 10 and 10, right? So we got a good idea that there's a lot of 10s here and a lot of zeros here. The middle 50% of the data, right, 25% is between 0 and 5. It's not obvious that those values are all 0, but we still get a better idea than we did from just the median or just the range of values. For this set, let's see here, 4, 4, 5, 6, 6. Gives us a good idea that this data is all fairly closely lumped. And here we've got 0, 5, 5, 5, 10. And you can definitely tell a difference here between the scores in section B and section D now, where here we can see that 50% of the class, at least 50% of the class, got scores of 5, right? Because this is a quarter of the data, and then this is a quarter of the data. Whereas here, the scores were definitely further out towards the ends. And so this helps reveal the spread of the data in a fairly small, concise way. Now, of course, with only 10 pieces of data, doing a 5-number summary is awfully silly. But if we had several hundred pieces of data here, the 5-number summary would definitely provide a nice, condensed way of looking at the data. So here we have our income data again, and we want to create a 5-number summary for this data. And so we need to figure out where our quartile 1, quartile 3, median, and min and max are. So minimum is fairly easy, right? That's our smallest value, and our maximum is fairly easy. That's the largest value. And now we need to find our quartile 1, quartile 3, and median. So for quartile 1, our locator will be 25% of our data. We have 100 pieces of data is 25. And since that's a whole number, we know we need to go between the 25th and 26th data values. So the mean of the 25th and 26th data values. For our median, and I think we've done this one before, but that's okay. For our median, right, we find half of our data values. Notice it's really the same as multiplying by 0.5 there. We come up with 50, which is a whole number, so we need the mean of the 50th and 51st data values. And then for quartile 3, let's see, it's going to come out to be 75, and so we need the mean of the 75th and 76th data values. Okay, so now we got to get counting. So here we have 6 pieces of data. Plus another 8 is 14, so together this is 14 pieces of data. Plus 11 is 25, and so here we've got 25 pieces of data. And then let's see, if we go down, plus another 17. Let's see, 17 and 25 is 42, so that's 42 pieces of data. And so notice now we've passed our 25th and 26th pieces of data. In this case, the 25th piece of data would have been here, right? Because that was, these added up to 25 pieces of data. So the 25th piece of data is 25,000. whereas the 26th piece of data is in the next category here, is 30,000. And if we find the mean of those, so if we add those up and divide by 2, we will get, let's see, what is that, 27.5 thousand as our quartile 1 value. So let's continue on here. So if we continue counting, let's see, if we go 42 plus our 19 there, gets us up to 61. So we have 61 pieces of data here. So that means that data values 50 and 51 both fell in the 35,000 category. So the mean of those is 35,000. And now, let's see here, 61 and 20 is 81. So we have 81 pieces of data if we go all the way down to here, which means the 75th and 76th pieces of data must have been in this category, in the 40,000 category. So 40,000 and 40,000. And if we find the mean of those, of course, we're going to get 40,000. And so it looks like our quartile 3 value is 40,000. So let's go ahead and write our five-number summary now. Our minimum is 15,000. Our quartile 1 value was 27.5 thousand. Our our median was 35,000. Quartile 3 was 40,000, and our maximum was 50,000. And so there is the 5-number summary for this income data. So when we create a 5-number summary, it can be useful to create a graphical representation of that information. And so earlier we calculated that from a set of female heights, we had a 5-number summary that looked like this. And we're going to create something called a box plot. So a box plot is, again, a graphical representation of the 5-number summary. So we're going to start by creating a number line. Now this should be a honest-to-God number line, evenly spaced. It needs to range from 59 up to 72. And so I'm going to go ahead and start it at 55, just for simplicity's sake. And let's see here, 56, 7, 8, 9, 60. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And so there is my number line, which is going to let me show my heights, which are measured in inches. And now we're going to construct our box plot. So the idea is at each of these values, I'm going to draw a vertical line. So I'm going to draw a vertical line at 59, at 62, at 66, and at 69, and at 72. Okay? Now I'm going to create a box ranging from quartile 1 to quartile 3. So starting here at 62, up to 69, with 66 in the middle. You don't necessarily have to label those values, but can come in handy. So this is why it's called a box plot, is because it has this box in the middle of it. And then we extend lines out from the box to the minimum and the maximum. Sometimes this is called a box and whiskers plot, because we have a box and then we have these sort of whiskers coming out on either side. In this case, going down to 59 and 72. Now, there are different types of box plots that are out there. Sometimes they won't actually extend all the way to the maximum or minimum, but in the type that we're going to look at, they do. And so there is our box plot. By the way, sometimes this here is called the interquartile range, the values that are contained within the box there. But that's not too important. Let's create one more. So here was the data from our income data, and let's create a box plot here. So once again, we're going to create a number line. Needs to range up to 50 from 15. So maybe I'll start here at 15, and maybe I'll just create every 5 here. So 15, 20, 25, 30. So 20, 25, 30, 35, 40, 45, 50. That should work. So there is our number line, and these are going to be incomes. And so we are going to, and I'm going to do a slightly different approach this time. I'm going to draw a box from my quartile 1 to my quartile 3. So there's my quartile 3. Quartile 1 is here, halfway between 25 and 30. And there's a box representing my, from quartile 1 to quartile 3. And now I'm going to draw in a line at the median, and then extend my whiskers out to the maximum and down to the minimum. And there is a box plot for our income data 5-number summary. So box plots can be particularly helpful when trying to compare two different data sets. So in this case, we have two different fast food restaurants, two different stores, and let's see what we can deduce from these box plots. So first thing we might look at is the median, and remember the score at the middle bar there is the median. And so store 2 has a smaller median, which means that remember, the median represents the score that divides the data in half, and so 50% of the time you're served in under 2.3 minutes here, and 50% of the time you're served in under 2.1 minutes there. So one could argue that on some measure of average, remember average is a not specific term, but by some measure of average, store 2 seems to serve a little bit faster. However, we also can notice that this range of values, because remember this represents 50% of the data as well, because these quartiles are dividing the data up into quarters. So 50% of the time here, you're served between 1.8 and 2.9 minutes. Here, 50% of the time, you're served between 1.1 and 5.7 minutes. And so the second store is a lot less consistent in the time, and we can also see that in this very large range. The first store seems to be more consistent in its delivery. In fact, 75% of people are served within 2.9 minutes. Only these unlucky 25% here were served in a longer time. So if you're feeling really lucky, you might try store 2, because you might get lucky and get served really quickly, faster than you might in store 1. But certainly, if you just can't spare a large amount of time, then store 1 might still be your better bet, since they seem to be a little more consistent in serving quickly. So let's look at another case. So the box plot here shows the birth weight of infants with severe idiopathic respiratory distress syndrome, or SIRDS. The box plot is separated to show the birth weight of infants who survived versus those that did not. And so what can we deduce from this, from these box plots? So we can tell that the birth weights of infants that died appears overall to be smaller than the birth weight of the infants that survived. In fact, we can see that the median birth weight of those that survived is about the same as the quartile 3 of birth weight of those that died. So this means that, for example, here, this is 25% of infants that survived. 25% of infants that survived were heavier than all of the infants that died. Likewise, notice that the quartile 1 here is bigger than the median here. Remember, quartile 1, this is 25% of the data, this is 75% of the data, so 75% of infants who survived had a higher birth weight than the median birth weight of an infant that died. So this gives us a quick, admittedly informal way to look at data and get some idea what's going on.